Hello everyone, I'm Xiaojun. I'm going to introduce our work on covering up anomalous accesses in electronic health record systems. And our team members are mostly from UIUC and Northwestern University, and many of them are also here, and you can talk with them later. So in this work, we will focus on EHR systems, and these systems will electronically record the patient's information. This can greatly help with the information sharing and improve the performance of hospital systems. However, such information sharing will also lead to privacy concerns. For example, if there are here an adversarial user, then he may steal the information of all the patients, and that is a privacy leak. Therefore, there is usually access control rules in EHR systems. However, people usually will not block an access in hospitals because blocking an access in hospitals may lead to a serious outcome if it is a false alarm. Therefore, what people usually do is that they will do post-hoc analysis to see if there are inappropriate accesses. For example, there were news that some hospital employees were fired because they accessed the information of some famous people coming to the hospital. And actually, many machine learning-based models have been proposed to do such kind of post-hoc detection. And our focus in this work is to see whether an adversary can bypass such kind of detection systems and make anomalous accesses without being detected by the detection systems. So first, we will introduce our data and our threat model. As introduced before, we will focus on EHR systems. In this system, a user is some staff in the hospital, such as a doctor or a nurse. And another component is an encounter, which is a visit of a patient to the hospital. For example, if I feel sick and go to the hospital, then all the information during this visit will be recorded as an encounter. And one user can access one encounter for certain information, and this will generate a bipartite graph. And we mainly focus on a private one-year dataset from Northwestern Memorial Hospital, and the dataset contains around 1 million nodes and around 27 million edges. And the features here we use include like user department or encounter types, and these are all actually node features. And to formalize our threat model, we, as the adversary, would like to make a desired access in the system, and we call it the target access. In order to do that, we hope that our target access will not be detected. So we will add other accesses, we call them the covering accesses, to disguise our target access. And our final goal here is that both the target access and all the covering accesses should bypass the detection. So this means that we also need to ensure the stealthiness of the perturbation that we injected. And here we mainly focus on graph neural networks because they are shown to have the best detection performance, but we will also consider other machine learning models in our experiments. So next, we will introduce how we design our attacks under different settings and their attack performance. In our work, we consider two types of attacks as shown here, the evasion and poisoning attack. This is the overall pipeline. We are going to break it down in detail. So as we discussed before, there will be some detection models here, like the graph neural networks. And the model is trained with some training data set during the training phase. And after the model is trained, the goal of the attacker is to make some target access, which is here the red access in the testing phase in the box. The key here is when the attacker launches the attack. If the attacker launches the attack during the training phase, which is the blue attacker here, then it is a poisoning attack. And otherwise, if it is during the testing phase, then this is an evasion attack. So first, we will look at the evasion attack. This means that the detection model is already trained here and will not be changed anymore. And we, as the attacker, will inject covering accesses during the evaluation phase, as here in the step 3. And here, the orange dashed accesses in the boxes are the access that we injected. After we inject them, we can see in step 5 that the accesses will be disguised. So the key of the attack here is how to inject the covering accesses. We propose an iterative algorithm and inject the accesses step by step. And in each step, intuitively, what we would like to do is to find the covering access that can mostly disguise our target access. However, recall that we also have the requirement that the covering access should not be detected by the system. Therefore, we will add two extra constraints that, first, the access itself should not be recognized as malicious. And second, it will not let the previously added accesses be recognized as malicious after we inject this access. And from the accesses that satisfy these two constraints, we will choose the one that can mostly improve the model prediction of our target access. And that goal can be interpreted as finding the node pairs that has the largest gradient value in the adjacency matrix with respect to the model prediction. And we know that this can be achieved with standard gradient techniques in attacking machine learning models. And here we show the results of our attack. The R attack column shows the final attack success rate, and the previous two columns, our target is the stealthiness of target access and covering of the covering access. So from the results, we can observe that our attack can achieve a pretty good attack performance. And here, with 50 accesses injected, we will be able to disguise over 75 of our target accesses, and all our injected covering accesses will remain stealthy and not be detected. So here we show an example of how our attack works. The adversary is a nurse of newborn and would like to access an encounter of some elder male, which is the red arrow here. So this will look very weird, and the system can easily detect it because the nurse previously only visits some, access some newborns, but here starts to visit some elder. So in order to disguise it, the nurse will first access some encounters of pregnant female. This will look good to the model because it is usual for a nurse of newborn to also access the information of their mother. And after several accesses, the system will gradually think that it is normal for the nurse to access other females. So the nurse will access some elder female. And after multiple accesses, finally the nurse can access the target elder male without raising the alert, which is the green arrow here. So this shows that our attack can gradually add new access patterns in order to bypass the detection. And then we will consider the poisoning attack. This means that we will inject covering accesses during the training phase, as shown here in the second step. And the model will be trained with both benign accesses and our injected covering accesses. And our goal is that the trained model will recognize our target access as benign during its evaluation time, despite the fact that our injected accesses will not exist in the testing phase. So in order to do this attack, our approach is to find the accesses that are similar with the target access. And we will inject them in the training phase and hope that the model can learn such kind of wrong pattern so that it will recognize our target access as benign. And here, we define the similarity as the embedding similarity between the nodes. So note that here, we have two relaxed assumptions. One is that we no longer require the stealthiness of the injected accesses. And second is that we also assume to have the knowledge of the testing phase when we do the perturbation during the training phase. This is something like the knowledge from future. We make this very strong assumption because we are going to show that even with such strong assumptions, it is still difficult to do the poisoning attack. And here we show the attack success rate here, again, as our target in the table, which is our attack success rate. We can see in the left table that the poisoning attack cannot work unless we inject a very large number of accesses, like 10K edges in 1 week. Alternatively, in the right table, we will show that we may also launch the attack if we add a larger training weight, that is lambda, on the injected covering accesses that we inject. But this is also unrealistic because we cannot control the model training process. So from these two tables, we conclude that poisoning attack is more difficult to accomplish. But why is that? We think this is an interesting open question to investigate. And here we identify two main reasons. The first reason is that the training and testing stage of the model is separated. So as we said before, the covering edges will only appear during the training phase, but not the testing phase. And the second reason is that it is difficult to change what the model will learn with only a small number of samples. So after training, the model will remain similar and can still detect our target access because in evaluation, there are no covering accesses. And for the ethics consideration, we would like to state that our study has been approved by IRBs. And since the machine learning for EHR system is still nascent, our proposed method will only pose some modest risk in the immediate future. Finally, we will introduce our experiments on a public data set. This is because our attack approach is actually general and can be applied to other graph tasks for like anomalous edge detection. And here, we choose a well-known intrusion detection data known as the LANL dataset. It contains 45 million authentication events, and around 500 of them are labeled as malicious with ground truth. And there have been several detection systems proposed for this task. And for attack, we use a well-known graph neural network-based system named Euler. And we apply our evasion and poisoning attack, which we introduced before, against the system and show the results here. The results show that we can observe a similar conclusion that evasion attack is successful, but poisoning attack is much more difficult. So we think this provides a way to reproduce our results on public data. That's all for our presentation. As a quick summary, we propose adversarial attacks against EHR systems by injecting accesses to disguise a target access. And we show that evasion attacks will be easier to launch under this threat model compared with poisoning attack. And we also apply our methodology on a public data set and observe a similar conclusion. Thanks for listening. Feel free to ask anything related.